Okay, so welcome back. So we were discussing about, process modeling in casting solidification. So we have discussed about, the governing equations, their derivations, their discretization techniques, and also the solution algorithms. So now we will start today's class with the, discussing about the different approaches that we take up to solve the flow physics and also the heat and mass transfer issues involved in case of casting solidification problems. So, to begin with, so the one of the prime model that is being followed worldwide is volume of fluid model. So, here actually in volume of fluid model, it is a surface tracking method used to simulate immiscible fluid interfaces such as the interface between solid and liquid phases during solidification, and the VOF model tracks the volume fraction of each phase in every computational cell, ensuring that the phase boundaries are accurately captured. What are the application? It is widely used for free surface flows, multi-phase flows and phase change phenomena like melting and solidification. And limitations are, it is difficult to handle complex moving boundary and is more suitable for flows where large deformations of the interface occurs. And the key feature is it captures sharp interfaces between phases. The minute points about the volume of fluid model. So, the main thing is that it basically solves all the governing equations like conservation of mass, momentum and energy. So, even if it is a multi-phase flow problem, so it solves only one governing equation. So, it is kind of a mixture model. So, it does not solve separate equations for individual phases present in that multi-phase fluid, whereas the second approach, that is Eulerian multi-phase flow approach. So, the Eulerian model is a multi-phase approach where each phase is treated as an interpenetrating continuum. So, and in solidification, both the solid and liquid phases coexist in a region, and the governing equations such as momentum, mass, energy, etc., are solved separately for each phase. So, not only the solid and liquid. So, in case of like a typical solidification, I will also discuss about a case study that we have solved solidification transport phenomena for a composite solidification in our group. So, you will see there that it may happen that solid can also contain multiple phases alpha, beta, etc. So, then the Eulerian model basically solves individual set of equations for all these phases. So, then it is although it becomes computationally heavy than a volume of fluid model, however, it can provide significant accuracy to estimate about the field variables which are which define the flow physics and also heat and mass transfer conditions such as velocity, temperature, pressure and viscosity, etc. And the application of Eulerian multi-phase flow model is that it is best for systems with distinct solid and liquid phases often used in crystal growth and casting. So, like VOF, Eulerian model also finds widespread application in casting solidification. However, there are some inherent advantages lying with both the models. So, like advantage, there is also some limitation in the Eulerian model because it requires the tracking of multiple sets of equations which can increase computational complexity, and the key feature, it treats each phase separately with phase interaction terms. So, so that is what the decision has to be made, that what kind of accuracy is on demand to solve the coupled flow and heat and mass transfer problem. So, although Eulerian model enhances the computational requirement, however, it can provide the correct estimations of the field variables, and also there is no separate interface tracking is required, not required in case of Eulerian model, like we have discussed in case of VOF model, because we are solving individual equations for individual phases. So, and they are basically interpenetrating, it is assumed, and so volume averaging technique is considered in case of Eulerian multi-phase flow modeling technique. So, here now let us discuss about the case study. So, this is the problem that is solved in our research group, and also it is published. So, here the study talks about investigation of the effect of minor additions of strontium in tune of 0.01% to so refine the microstructure of magnesium silicide, which is a primary phase in the composite that we developed. So, basically it is aluminum 15 Mg2Si 4.5 Si. So, that is a novel composite that we have developed. And we also have got patents awarded for the composite. So, basically here the goal was to study the solidification transport phenomena for this composite during semi-solid slurry generation. So, here basically two primary grains evolved. So, the one is primary Mg2Si and another is alpha aluminum. So, why we are calling two primary grains? Because Mg2Si is the first phase to nucleate from the liquid melt to composite melt. So, that is why we are calling it as primary, and in case of aluminum we are still calling it as primary because it is the dominant phase present in the solidified composite. So, that is why we are considering. So, that is why we are depicting that we have two primary phases in this composite and analogous changes. So, along with the formation and morphological evolution of these primary grains due to the addition of strontium, which has been captured effectively in this Eulerian multiphase flow model for solidification transport phenomena that we developed. So, here also analogous changes in thermophysical properties of the generated semi-solid slurry has been estimated in view of product and process development, and it is to be noted here that the strontium addition within the composite primarily aids to modify the primary Mg2Si grains to cubic form compared to that of dendritic shaped ones in case of conventional untreated composite by virtue of poisoning effect. So, which leads to so how basically it is making the Mg2Si grains into assuming the shape of cubic. So, by basically by virtue of poisoning effect. So, which leads to the restriction of the growth of primary Mg2Si crystals in a dendritic manner. So, further shear flow of the melt along the cooling slope, here cooling slope has been used as a slurry maker. So, what it does, it basically imparts a shear stress along the melt flow in the direction of the melt flow. So, because of the exerted shear stress, basically it facilitates crystal fragmentation, and thereby and also it promotes heterogeneous nucleation, and thereby it basically facilitates refined primary grain formation and also leads to the generation of semi-solid slurry. So, here so in this solidification transport phenomena, the problem that we have solved using Eulerian multiphase flow model. So, here basically the shear flow of the melt along the cooling slope is considered, which transforms cubic shape primary Mg2Si grains that are generally originating due to the strontium addition into near spherical grains. So, now we will discuss about the conservation equations that we have solved for the each phase, like we have discussed already about the two primary phase, that is primary Mg2Si and aluminum, and also the parent liquid phase. So, basically here this Mg2S aluminum and Mg2Si are the product phases and also the parent phase is the liquid composite melt. So, so basically so then how many phases are there? So, basically it is 1, 2 and 3. So, basically we solved 3 set of equations, 3 set of governing equations for for the present solidification model. So, then so mass conservation equation between the liquid and solid phase. So, here it is not shown separately for both the primary grains. So, rather it is shown only for liquid and solid. So, basically the effect will be additive. So, del T FL rho L plus grad FL rho L UL is equal to MSL, that is the source term during mass exchange liquid to solid transformation, and here it is the the relationship between the MLS and then this is the conservation mass conservation equation for solid phase, that is del del T F s rho s plus grad I mean F s rho s U s is equal to M L s. So, basically M L s is related to M S L in this way. So, M L s is equal to minus M S L. Okay. And then so the momentum conservation equations are also solved individually for the parent liquid and the product solid phases, and although for simplicity here it is only shown for as a for one solid, similarly it is solved for another solid phase also. So, here the momentum equations, so all those I mean forms equations we have discussed earlier also in this course, but for your I mean ease of understanding I am repeating this. So, basically it is the I mean del del T F L rho L U L plus grad F L rho L U L into I mean U L. So, it is a I mean a substantial derivative and is equal to minus F L I mean grad P. So, it is the pressure force, and then so this is the viscous force I mean grad tau L plus this is the gravity I mean or you can say body force. So, these are basically the body force and then the source term of the momentum equation. So, it is basically the other body forces are clubbed into the source term. Okay. So, I mean so then so these are so then basically this pressure and viscosity this comes under surface forces, and basically so these are this is the body force that is due to gravity and this is the source term, and similarly for the solid phase also the momentum equation is depicted, and then energy conservation. So, it is so del del T rho F L rho L and H L. So, why this term F L is coming over here? It is basically depicting the liquid fraction present in the while solidification. So, how they are basically related here? So, here F L plus F s is equal to 1. Okay. So, this is the conservation of mass that is maintained in the solution of these governing equations, and then so the energy conservation equation for the liquid phase takes the form del del T F L rho L H L. H L is the heat transfer coefficient for the liquid. Sorry, H L is the enthalpy of the liquid H L plus grad F L rho L U L H L. U L is the U velocity is equal to grad F L K L. So, basically this is the thermal conductivity of the liquid and delta and grad T L. So, this is the temperature of the liquid plus Q S L. So, basically this is the source term of the energy equation for liquid. Okay. And then the second equation, that is it is solved for the solid phase, and then the species conservation. So, species conservation also so it is similar terminology. So, basically this is you can see del del T F L rho L C L plus grad F L rho L U L, that is the U velocity of the liquid multiplied by C L. C L is the concentration of solute in liquid. So, concentration of solute in liquid. So, basically it is and then CSL. So, it is basically the source term for the species conservation equation. Okay. So, similarly the species conservation equation for the liquid phase and species conservation equation for the solid phase. So, this is are solved, and then here the so that these terms, that the shears viscous term is expanded over here. So, tau L is equal to rho mu L F L. Mu L is the dynamic viscosity of the liquid, F L into grad U L plus grad U L transpose. Similarly, for the shear force of the solid phase, shear stress of the solid phase, tau S bar is equal to mu S, that means the dynamic viscosity of the solid phase, F s solid fraction, multiplied by grad u s solid velocity plus grad u s transpose. And then where H L, that is the enthalpy of the liquid, is basically can be expressed as H L is equal to integration T reference to the liquid temperature at any given instant, that is T L. So, C P L specific heat of liquid d T plus H L reference. So, the reference enthalpy of the liquid, and then H S, it is the solid enthalpy, which is again similarly expressed like liquid, that means integration T reference to T S C P S solid specific heat d T plus H S reference, that means reference enthalpy of solid. Okay. So, then here also we have also introduced the nucleation term. So, nucleation source term basically. So, it is also giving the nucleation rate. So, which is equal to d delta T by d T n max by that is the maximum grain density n max. Okay. So, basically it is a undercooling based model which is basically implemented over here to understand the solid formation mechanism during the solidification of the composite. So, n max divided by root pi delta T sigma exponential minus half delta T minus delta T n by delta T sigma whole square. So, here so basically CLS is equal to minus CSL, the species exchange rate kg per meter cube per second, and similarly which can be subdivided as CLS drag. So, CLSD, so species diffusional flux, and then CLSP, that is species exchange due to phase change. So, these are the and similarly the source terms of the momentum, that is ULS, which is a summation of source term due to drag between liquid and solid phase, and source term of momentum due to liquid to solid phase change, which is further shown like this. So, like ULSP is equal to U asterisk bar into MLS, and ULSD, that is the source term due to drag between liquid and solid phase, is equal to KLS into UL minus US, that means liquid velocity minus solid velocity. Solid velocity. So, the relative velocity between the liquid and solid phases generally triggers because of their differences in their viscosity that we have discussed earlier. So, then and similarly for species we have discussed, it is basically the CLS is equal to summation of CLSD plus CLSP, again similar like. So, this is because of the drag and this is because of the phase change. Okay. Phase change, and this is because of drag between the solid and liquid phases. So, CLSP is equal to C asterisk MLS, and CLSD so the source term for species due to the drag between liquid and solid phases is neglected in the model to enhance simplicity. So, then this is the final form. So, QLS is equal to QLSD plus QLSP, where QLSP is equal to H asterisk MLS and QLSD is equal to H asterisk multiplied by TL liquid temperature minus solid temperature. Okay. So, these are the different source terms for the momentum equation, species conservation equation, energy conservation equation, and the source term of the mass conservation equation, that is MLS, which is expressed as G alpha, that is grain growth rate, into delta C into n pi ds square into rho s solid density into FL, that is liquid fraction. Okay. So, we have already discussed about the nucleation so basically we consider a Gaussian nucleation distribution model. So, thereby we are basically estimating the nucleation rate, that is capital N, and then in the mass transfer equation you can see that MLS is equal to G alpha T minus TF by M. M is the basically slope of the liquidus line minus CL into N, it is the grain density, into pi ds square, that is the solid diameter. So, grain diameter of evolving solid particles. So, in this study we have evaluated the grain diameter of both the primary solids that is Mg2Si and also alpha aluminium separately. However, for simplicity it is only shown for one solid phase into multiplied by solid density into 1 minus Fs. 1 minus Fs is nothing but Fl, because we know that Fl plus Fs is equal to 1. So, then 1 minus Fs is equal to Fl. So, this is what you can see over here, and so this is this work I mean our latest publication also there, you can see. I will name the paper a little later. So, before going to the research results, let us discuss about thermosolutal convection. So, thermosolutal convection occurs due to local density differences arising from temperature inhomogeneity, concentration inhomogeneity, and as well as phase change. So, shrinkages occur during solidification as a result of volume losses balanced by shrinkage flow. So, shrinkage flow is driven by pressure gradients. Okay. So, modeling thermosolutal convection, how can we model this? So, temperature and solute variations are coupled with the mass and momentum conservation equations. A free moving melt surface forms at the top due to shrinkage, and air fills the feeding flow region where when the cooling rate of the mold surface exceeds the cooling of the top melt surface. Okay. So, so then density definition for thermosolutal convection. So, the liquid phase density is defined as this expression, that is rho L T c is equal to rho 0 1 minus beta t into t minus t 0. So, here beta t is equal to thermal expansion coefficient, okay. Beta c is equal to solutal expansion coefficient into so here and T c are the current temperature and species mass fraction. Okay. So, this is basically the density. So, this is the density for thermosolutal convection, and then so they where basically the density change due to thermal expansion, due to temperature change, and also density change due to the change in the solute concentration is both considered, and that is why it is termed as thermosolutal convection, and basically the shrinkage largely depends on that. So, that density change. So, we we generally assume that the liquid and solid phase density to be constant, but it has to be ideally it has to be considered the variation of density as a function of temperature as well as solute content in the melt, so that the effect of thermosolutal convection can be simulated in the solidification transport phenomena model, the process model for casting solidification. So, additional modeling details are the Bose-Skew approximation, which applies for the momentum equations, and gravity terms, buoyancy force are included in the momentum equation. So, these are the additional considerations. So, now we will discuss about the different solvers that we use for solution of the conservation equations that are involved in solidification transport phenomena. So, so this is basically this is the widely renowned solver package for computational fluid dynamic problems, that is Fluent, that the so that is also works on these principles. So, then what the density based solver? So, the density based solver basically solves the governing equations of continuity, momentum, and energy and species transport equations simultaneously, that is coupled together. So, governing equations are additional scalars will be solved afterward and sequentially. Okay. So, that is segregated from one another and from the coupled set. So, these are like special equations. So, for example, what can be the additional scalar? So, additional scalar, a representative example is grain density. Okay. So, like we have discussed about the model Eulerian multi-phase flow model that we just discussed before. So, we have also solved that, but we solved the multi-phase flow Eulerian multi-phase flow model by considering pressure based solver, but this is the intrinsic benefit of the density based solver is that it can basically facilitate solution of all the governing equation, that is conservation of mass, momentum, energy, and continuity equations. So, all known governing equations, they can be solved simultaneously together. So, whereas in case of pressure based solver, mostly it is they are solved in a segregated or decoupled, I mean the sequential manner. We will come to the pressure based solver later. So, let us focus on density based solver now. So, here, so as I told you that I mean after solving the simultaneous after solving these known governing equations simultaneously, the additional equations for scalar transport equations like grain density, or it can be something else as well. So, they I mean can be solved sequentially, that is segregated from the coupled set of main governing equation. So, because the governing equations are nonlinear and coupled, several iterations of the solution loop must be performed before a converged solution is obtained. Each iteration consists of the steps illustrated in and outlined below. So, number 1 is update the fluid properties based on the current solution. If the calculation has just begun, the fluid properties will be updated based on the initialized solution. Number 2 is solving the continuity, momentum and energy and species equations simultaneously. Okay. And then number 3 is where appropriate solve equations for scalars such as turbulence and radiations using the previously updated values of the other variables. So, you can also couple grain density with this, which is applicable in case of solidification transport phenomena. Okay. So, then after that, when interface coupling is to be included, update the source terms in the appropriate continuous phase equations with a discrete phase trajectory calculation. So, this is so this is basically a intrinsic to the density based solver, and then after this we need to check for convergence of the equation set, and these steps are continuous until the convergence criteria are met. So, this flow chart of density based solver gives you the idea as a whole. So, you can see so first is update properties that we have discussed at the beginning, that is update the fluid properties based on the current solution, and once the properties are updated, then simultaneous solution of continuity, momentum, energy and species, that means all 4 governing equations responsible for depicting the flow physics and heat and mass transfer and solute segregation conditions in case of solidification transport phenomena. And then, so once they are solved, then sequentially or in segregated manner scalar transport equations and also for turbulence and as well as for radiation. So, these are solved in case of density based solvers, and then once the solutions of the primary variables or field variables like pressure, temperature, velocity, they meet the convergence criteria laid in the model, then if they meet, then the calculation stops. If they does not meet, then the iterative loop begin goes back to the first step. So, this is how it works, the density based solver. And now, the coming back to the pressure based solver. So, the pressure based solver uses a solution algorithm where the governing equations are solved sequentially, that is segregated from one another. Okay. So it is basically exactly the opposite of what we have discussed in case of density based solver. There we have discussed about solving all these equations in a coupled manner. Here they are solved in segregated manner. So, because the governing equations are nonlinear and coupled, the solution loop must be carried out iteratively in order to obtain a converged numerical solution. So, in the segregated algorithm, the individual governing equations for the solution variables, that is u, v, w, p, t, k, epsilon, etc., are solved one after the other. So, each governing equation while being solved is decoupled or segregated from other equations, hence it is the name. So, the segregated algorithm is memory efficient. That is why pressure based solver is being used widely. We also use this for our calculation of solidification transport phenomena for casting, welding and even additive manufacturing problems. So, basically the segregated algorithm is memory efficient, since the discretized equations need only be stored in the memory one at a time, and not all the equations need to be stored in the memory at once like it is needed in case of density based solver. So, however, the solution convergence is relatively slow in as much as the equations are solved in a decoupled manner. So, I mean, so it may take some time, but it can give you accuracy. So, in case of pressure based solver. So, with the segregated algorithm, each iteration consists of the steps illustrated below. So, number 1 is again the same, the updating the fluid properties, that is density, viscosity, specific heat, including turbulent viscosity, which is also called diffusivity based on the current solution, available solution. And then number 2 is solving the momentum equations one after the other using the recently updated values of pressure and phase mass fluxes. So, one after the other means, like I have discussed earlier in the Eulerian multiphase flow model. So, we are solving the momentum equations for different phases like liquid and solid phases. So, they can be solved no, in spite of solving them simultaneously, they get solved actually sequentially. Okay. So, one after the other. So, then number 3 is solve the pressure correction equation using the recently obtained velocity field and the mass flux. Number 4 is the correct phase mass flux values, pressure and the velocity field using the pressure correction obtained from the step above, that is step 3. And then solving the equations for additional scalars, like we have discussed grain density, it can be turbulent quantities, it can also be like radiation quantities and other, and also energy and species equations are also solved later on after the pressure pressure correction equation and the momentum equation. Okay. So, update the and then next step is the updating the source terms arising from the interactions between different phases, that is source term for the carrier phase due to discrete particles, and then finally, the checking for the convergence of the equations, whether the field variable are meeting the convergence criteria or not, and if they are not meeting, then it goes back to the first step, like we have discussed in case of density based solver. So, whatever I have discussed in the previous slide for pressure based solver. So, it is shown with the help of this flow chart. So, that is you can so then you can see that first the momentum equation is solved, then the pressure correction equation or the continuity equation is solved, and then in the third state the species, energy, and as well as turbulence or other scalar equations are solved, and prior to that mass flux, pressure, velocity values are updated, and then the convergence criteria is checked for the output findings. So, with this I am stopping for this class, and we will start in the next class with the boundary and initial conditions that need to be given in a typical flow and solidification problem to get the accurate estimation about the temperature and other field variables like viscosity, melt velocity, etc. Thank you.